very common variation in our species. In fact, about 60% of human X chromosomes have the serine version, about 40% have the alanine. So in this room, for example, although many of us think we are, quote, color normal, actually we divide up perceptually into different groups, depending which polymorphism. Now for the main course, the evolution of primate color vision. So first, how do we know that an animal has color vision? Obviously, with a person, they can tell.
Of unfolded molecules, this happens to be ribonuclease again, as a function of some denaturing property, in this case temperature, but it might well have been denaturing concentration. And what you're seeing here are a number of different kinds of tick marks. Each of these kinds of tick marks represents a different probe of the native conformation. Almost all of them are spectroscopic probes. One of them happens to be intrinsic viscosity. They're very different in kind. And yet, after suitable normalization, all these probes fall on the same unfolding curve. So what that suggests is that this is a highly cooperative process. To a physicist, it would look like a first-order phase transition. And what you're seeing is one of these sort of all or none kind of changes, so that if you would go to the midpoint of this curve, instead of seeing the molecules halfway unfolded, what you would see is half the molecules are still fully folded and half the molecules are still unfolded, completely unfolded, and the population of intermediates is absolutely negligible. So that gives rise to this idea that many small proteins fold in this kind of two-state manner. They're either folded or unfolded with a negligible population of intermediates. So the current paradigm that comes from all of that is that you go from the random coil, the unfolded population distributed over this broad energy landscape, to the folded population. And the only way that you can explain that is that the native conformation is very low in energy compared to all the others. So the native state corresponds to a minimum energy conformer. Now we know, and Anfinsen was very careful to articulate, that that means minimum in Gibbs free energy, which includes the free energy of the entire system, including the solvent. But people have taken a shortcut in their thinking, which goes something like this. I'll caricature it again. When the protein folds, it folds to a single conformation. We know it's rattling around in wells a little bit. We know that it doesn't stay 100% folded, that it's fluctuating, it unfolds, it's partial unfolding, it's complete unfolding. But at any given instantaneous moment in time, 99.999% of the molecules are folded for a typical globular protein. And so what we argue is, well, basically it forgets it had any entropy to lose. And so what it must be doing is minimizing its energy. The entropic component of this is largely gone in the folded conformation. And it remains in the folded conformation, so clearly that's a stable conformation. Furthermore, the unfolded state is a featureless landscape. People have explored this. We'll get back to that in a bit. Since the unfolded state is a featureless landscape and there are no stabilizing interactions there, the folding must arise on the n side of this U to n equation. All backbones are essentially the same, so it's really the side chains that have to discriminate the correct fold from all other folds. The predominant organizing interactions are hydrophobic. It's the hydrophobic effect that folds, and these organizing interactions remain visible within. And so it's given rise to this current metaphor that under the unfolding condition, the protein can explore this broad energy landscape, but it's rather undifferentiated. And then, as it loses conformational entropy, it falls down to this steep minimum where favorable enthalpic interactions kick in, but entropy, which is represented by the width of it, is lost. That's the paradox. And now we're going to click. So, we move on to the first question, really whether the native state corresponds to a minimum in energy. So here is this Ginsberg and Carroll experiment represented diagrammatically. Here what you're doing is denaturing the protein, and the fraction of unfolded molecules goes up as the denaturing concentration goes up. And if this is two-state, as we tend to think for these small molecules, and which can be proved rather rigorously for a large number of molecules, then what that says is that the free energy difference between the folded and the unfolded state is given by minus RT times the log of the concentration of the native population divided by the unfolded population. And at this midpoint,